So today let's talk about friction with an Atwood system. And that eventually we're going to get a little bit more complicated with respect to what's happening with this block. So, so look at what we have here. We've got a block resting on the table. We've got a string connecting it to a weight. And since there is no acceleration, then the system's got to be in equilibrium. So we have our force diagrams of the situation. So here's our wooden block. All right. Here's this black weight hanging down. And if we look at the force diagrams, this wooden block has the normal force pushing it up. It's got weight pushing it down. The tension in this string is pulling it this way, and there's some static friction that is holding it back. That block down there has weight pulling it down and tension pulling it up. So there's our force diagrams. Now, if we want to think about the system, then the weight of that thing is trying to pull the block to the left and that weight down. And the friction of this thing between the table and the block is trying to pull the block to the right and bring that weight up. So our system diagram looks like this, with weight going this way and the force of static friction going this way. Now, the force of static friction, again, is always equal to the coefficient of static friction times the normal force. We're going to talk about this math here in a second. Notice the tension forces go away when we're talking about the system, because it's acting in two different ways within the system. All right, so the sum of the forces acting on the system is 0. Why? Because the system's not accelerating. Now, that presents us with some mathematical problems. What happens if I put this weight on top of there? We haven't changed that block down there. So this weight of the black weight that is pulling this system down and to the left, depending on whether you're talking about the hanging black block or this wooden block, and the friction force is still pulling this thing this way. Now, it seems a little weird, right? I add this thing on top of the block. So technically, I've increased the normal force acting on the block. Well, the only way for this thing to be in equilibrium is for that weight and this friction force to be equal to each other. Well, they're equal to each other right now. So if I take mu times the normal force, it equals that weight. Well, if I do that, I've made the normal force bigger, yet it still equals the weight. How can that possibly mathematically be? Well, that can mathematically be because this coefficient of static friction is a variable coefficient, which makes the force of friction static variable. So we can manipulate the math a little bit. This thing technically varies up to a maximum amount. Now, if I go back to my original situation here, again, the sum of these forces is 0. Well, how can I get this system out of equilibrium? Well, I can get the system out of equilibrium, not by increasing this, right? Because you're never, no matter how much weight I put on here, friction never pulls this system back that way. It just doesn't operate that way. It doesn't work that way. However, clearly, I can add to that weight and cause this situation here to accelerate. So if I make that weight bigger, then all of a sudden my situation changes a little bit. And now I have an acceleration of the block. How did I do that? Well, I made this bigger than the maximum value of that static friction. Now, if I reset this, to and hang my small black weight here, now we're in equilibrium. If I add that thing, we're still in equilibrium. Why? Well, because I can only increase this to a particular amount because that's variable, equals that weight. Now I add this thing on here. Again, we're still in equilibrium. But if I take this thing off, I'm decreasing the normal force and therefore decreasing the static friction force. So then my force bringing this block to the left and that weight down is bigger than my friction force, and I get an acceleration. All right, so how does that work mathematically? All right, well, look at, again, this weight force has to be bigger than this static friction force. So now the sum of the forces on my system must equal the mass of the system times the acceleration. What forces are acting on this system? The weight of the black weights minus the force of static friction must equal the mass of the system times acceleration. In reality here, once this thing starts to slide, it's really not static friction anymore. It is kinetic friction. So, you know, what's this? I'm just going to call this the mass of the black blocks, right? So this is M times the black weights times G minus, what's my friction force there? Well, it's mu times the normal, but that's really mu times the weight of that, right, in this particular situation. So that's my coefficient. Again, once we slide, that's going to be different than that. It's going to be my kinetic coefficient times the mass of the wood times G equals, now what's the mass of my system over here? It's the mass of the black block plus the mass of the wood times that acceleration A, right? And I could solve that thing, for A. And, all sorts of different stuff can happen here by changing the various things, right? So in other words, if I increase this, I'm making the left side bigger. If I were to put, and if I make the left side bigger, then my acceleration is going to get bigger. But if I put some sandpaper underneath here, I'm going to increase this. Well, this coefficient. Well, since I'm subtracting that, I'd be making the left side smaller, and then therefore my acceleration would get smaller. So there's all sorts of different manipulations that can happen. Okay, but it all goes back to this friction force and how it compares to the weight of the blocks. So now let me show you something else here. All right, so let's do this. Let's add this thing, right? That's our little thing we saw from our Atwood video before. So now again, we know that the static friction force is equal to this weight that's going down. But that's a variable force, remember. So if I increase this, I'm still in equilibrium. So if I increase this, that friction force must have just got bigger. How did it get bigger? Well, again, this coefficient here is a variable coefficient, so that thing can change. It got bigger to make mu times that normal force equal to this weight. Well, if they're no longer imbalanced, if this thing becomes bigger than that, then we get an acceleration like this little setup here. Well, we can throw this out of equilibrium by increasing this weight, which is what we did before to get this. Or now in this particular case, we've got the ability to decrease this. So watch what happens when I take this big silver thing off. Again, this is currently equal to this. I can throw this out of equilibrium by increasing this or decreasing this. You've already seen me do this, increase this. Well, now let's decrease this and see what happens. So if I take this silver thing off, look at what happens. The block with the little party favor on it accelerates this way. Well, now let's examine what's going on there, because that is pretty intricate unto itself. So now here's that setup. As this block is accelerating, the tension on the wood block is pulling it to the right. The friction force, it's now a kinetic friction force. Now I label it F sub 1, all right? Because it's the friction force between the table and the wood block. So the tension in this string pulls this forward. The friction between the table and the wood block pulls this thing backwards. And that causes the block to accelerate this way. Well, guess what else is on top of it? The party favor is on top of it. When the block accelerates, the party favor comes with it. But the string's not pulling on the party favor. And the friction between the table and the block is not acting on the party favor. So what is it that is pulling the party favor this direction? That's the weird part. Friction between these two things actually pulls the party favor to the right. Now that's weird, because normally we think friction is opposing motion. Now I might have my rights and lefts mixed up because the camera flips things on me when I'm videoing this, right? So if we're accelerating this way, it's actually the friction between the party favor and the block that causes the party favor to accelerate in this direction. But wait a minute, friction is supposed to oppose motion. Well, remember, it opposes motion or desired motion. Now, this is a tricky part, right? Because motion is always relative. So really, what's the desired motion of this party favor when it's at rest? The desired motion of the party favor is to actually stay at rest. Well, if this wood block gets forces exerted on it, its desire might be to move in this direction, but the party favor's desire is to still stay still. Well, then relative to the block, it would actually be moving in this direction, right? So if the block moved in this direction and the party favor stayed still, technically with respect to the block, the party favor would be moving in this direction, which means friction would oppose this desired motion by bringing the party favor with it. Now, that is a second force of friction. So I'm going to label that F sub F with a 2 on it. That is not the same friction as this. This is the friction between the block and the tabletop. This is the friction between the party favor and the block. And that is what accelerates and pulls that party favor in this direction. Now, one other weird thing is that technically, right, if there's friction between this block and the party favor, and it's pulling the party favor this way, so the block is exerting a friction force on the party favor going this way, then the party favor's got to exert a force on the block. Well, that's an action-reaction pair. So if the block's exerting a friction force on the party favor going this way, then technically the party favor actually exerts a friction force. Again, it's labeled as FF2 on the wood block going this way. So there's two friction forces acting on the wood block, one from the table, one from the party favor. Our biggest key here is it's now friction that is pulling the party favor, causing it to accelerate. All right, now I got one more thing to show you. So let's think about this. Let's put this thing all back together again. I got my big silver weight. I'm gonna hang these two little things with it right here. Actually, let's just hang. Yeah, let's do that. We'll put this here. Okay, so let's set this all back up again. Last thing here for our little lesson. Okay, so what do I got? I'm back to my original situation, right? I'm back to my original situation. So I have, I'm gonna take one of these things off here. I have this force of friction. I have this force of friction pulling the system this way. And I've got the weight going that way. They're in equilibrium. I pull this thing off. They're still in equilibrium. Again, how did that happen when I lowered the normal force? Well, I lower the normal force, but this thing can adjust to make sure that the static friction force is equal to the weight. Because right now those things are equal to each other. Now, what did I do before, right? I hung this tiny little weight here, and it accelerated the whole system, and it brought the it brought the party favor with it. Now watch what happens here when I hang this giant weight off of the end of here. All right, now let's think about this. We talked about this. If I make this super big, that's going to cause a really big acceleration in this direction. If I make that big, that's going to make the left side of this big, which causes a big acceleration for us. Watch what happens to that party favor, though, when I do this. Because remember, what's trying to pull that party favor forward? The friction between the party favor and the block is trying to pull the party favor forwards. Watch what happens when I load this up with a bunch of weight. Watch what happens to my party favor. The party favor did not accelerate with the block. How does that work? Well, again, what's pulling, let's set the party favor back up on the block. What's pulling the party favor to this in this direction? The force of friction between the party favor and the block. Now, when I add a bunch of weight over here, I'm not changing the coefficient or the normal force over here. This force has a limit. Now, if the party favor is accelerating, then the sum of the forces acting on the party favor has to equal ma. So the sum of the forces, I'm going to call it P on the party favor, must equal the mass of the party favor times the acceleration. Now, what force is causing the acceleration? Well, we've got it labeled as F2 must equal the mass of the party favor times A. As long as there's an acceleration. Well, guess what? When we increase that weight over there, we are jacking this way up. But this has a limit. And if M times A is bigger than the limit of this force of friction, then the party favor doesn't actually get accelerated. The amount of friction that it can provide only gets an acceleration up to a particular limit. And if the acceleration passes that limit, then this thing doesn't accelerate forwards anymore. It just falls off the block.